Hello and welcome to Rustacean Station. I'm your host, Alan Wyma, and today we have a Brenden Matthews with us, who is the author of, I always mess up this author, the name of the book, but it's Code Like a Pro in Rust.
That's right.
When I first read the title, I didn't really know what it was about. I thought maybe this is like some tips and tricks or syntax stuff or something. But actually, it's much more than that. I'm not going to talk too much about it. Let me let Brenden talk about himself and also talk about the book. So why don't you go ahead?
Sure. Yeah. Well, thank you for the introduction. My name is Brenden. I've been writing software in one form or another for I don't know, better part of 20 years, I guess. I basically taught myself to write code probably at the age of 12 or so. When I got into IRC, actually, if anybody remembers IRC, I don't know. But the internet has changed a lot since then. But, programming hasn't really changed that much, even though we have a lot of new languages. In a lot of ways, it's sort of the same stuff. So that's me in a nutshell. Yeah.
Yeah, where did the idea to write this book come from? And actually, like I said, I think the title, at least for me, when I read it, was I don't know, like I got a different feeling from it, but I can still understand the title, right? Like, what was kind of where the idea come from?
Yeah, so I didn't start out with the idea to write a Rust book necessarily. I was approached by the publisher that I'd actually previously agreed to write a book, and then I realized I just couldn't devote the time to it at the time, and so I backed out of it. And I'd always wanted to write a book, and the publisher approached me and they asked me if I wanted to write a book about Rust because I've published a few blog posts and whatnot on the subject, and they thought that there was a good opportunity there to sort of take the same line of thought and turn it into a book. So that's how we got going. And originally, the book as it is today isn't exactly what we started out with. It kind of evolved into what it is. But the main thing I wanted to do was write a book for. Basically, write the book that I wish I had when I was trying to learn Rust, with the hope that someone with a similar background to mine, being a person who is already pretty experienced in programming in general and wants to get up to speed on Rust quickly, but doesn't need like an exhaustive lesson in programming or syntax or anything. Basically, you just want to go from like having the basics, like, you can compile hello world and like maybe build something simple, go from that to actually having something that's closer to production grade, or at the very least, like try to fill in all the blanks that exist anytime you're trying to learn a new programming language that make it really hard to actually like finish something properly. Right? That's the book I wanted to write. And there's already a bunch of Rust books, but I think most of them are either introductions to Rust or maybe like specific like this is how you write a web server or whatever in Rust. And I didn't want to do that kind of book either. So yeah, that's how we got here.
Yeah, what I find to be the most difficult part about Rust is that I want to write my code like a Rust developer should. There's always like this kind of idea like, this is very Pythonista, or I forgot the term is that they use, or this is very, I think the term that they use in Rust is like Idiomatic Rust.
I think.
Yeah, Pythonic. And yeah, Pythonic. And I don't remember if there is a one for Ruby, but for sure there's one.
I don't. Mm-hmm. Yeah, I don't know if there's an accepted term, but I write Rustacious. I don't know if anyone else uses that or if that's caught on. I haven't seen anyone else write it, but like that's what I write, Rustacious. There's like a Rustacious way to do things. I like it because it fits with like the crustacean. Sort of, it's like a bit of a play on words there.
Yeah, I think what I usually hear is idiomatic rust, which I don't know if that's actually the right term. I hear that a
Yeah.
lot all the time.
Yes, I would say that's like the generic way. Like you could say idiomatic Python or idiomatic C or whatever. That would apply generically. But yeah, I mean, figuring out how to get there is tricky, and that's definitely one of the things that I try to communicate in my book or like guide people towards. Not that I consider myself like an authority, and there is no authority on like what is the correct idiomatic way to do things in Rust, but there are definitely things that work and things that don't work, and there are definitely things that you should and shouldn't do. And as with any programming language, just because you can do a thing doesn't mean you should do the thing, right?
Yeah, I think the difficult part for me is no matter what, there's always multiple ways of doing the same thing. Even within Rust, I mean Python, they say there's only one way, but there's still multiple ways. Just maybe less likely. But with Rust, yeah, I mean there's more than one way, right? So like you can pattern match. Like if you only want to unwrap the value, I can use unwrap. I can use expect with a message. I can even use pattern matching if I want to. I could be very clear. I mean, even like the question mark operator, right? There's more than one way to. You can use it. You can just do it by hand. I mean, there's more than one way to do this kind of stuff. So, like, the question is like, how can I best learn, how to actually write idiomatic code? Like, do you think your book actually would address something like this, or this is something that just happens over time?
Yeah, these are exactly the sort of questions that I try to answer in my book. Um, using your example, right? You have unwrap and expect, which are like related, and they're slightly different. And like there's a case where you want to use unwrap, and it's a fairly narrow case, and it's basically whenever you know that unwrapping the thing is not going to blow up, right? Then you can just use unwrap. But most of the time, like, problem with unwrap is that it's easy to use because you get like you write something that say returns an optional or result or something, and you start to get a little lazy or complacent, and you're like, well, it's probably okay. I'm just going to unwrap it, and maybe I'll come back here and fix it later, right? And like if that's the logic in your brain, then you're starting to make a mistake, because like that's how you create bugs. One of many ways you can create bugs, but I would say that is why expect exists, right? So expect is slightly different. Expect is when you are pretty sure that the thing should always be what you expect it is, right? Hence the name expect. Right? Like if I've got a string or an option that contains a string, and like there should be a string in there, but I have to get it out, then you can use expect, and it basically behaves the same way as unwrap, with the exception that if for some reason it's actually not doesn't contain what it something, then it blows up, right? It blows up in a way that is like the same as like an assert or something in C. It's basically like you're saying like, if this is not here, then raise an error, right? And that's a little different from unwrap, even though like I guess the end result is effectively the same, but it's slightly different. But it's a bit. You can definitely debate this stuff. Although most of the time, right? Like if you have something that could be present or not present, then you should be handling both cases, right? Like it's either present or it isn't. And if it is present, then rather than unwrapping it, you should be just like pulling that thing out and then dealing with it on its own, essentially, right? So in that case, you'd probably pattern match most of the time.
Yeah, that makes sense. There's also so many different other like helper methods too. Like you can also use if, and I think there's like a dot is okay. I forgot when unwrapping and expecting could be used, but there's all these kind of other helper methods. So you can also say if whatever that is okay. That can also work too, right? There's just so many different ways, and I guess it kind of depends on how you think about writing what you want to write, and then that would kind of bring itself out.
Yeah. I mean, with stuff with something where it's basically like two states of like either present or not present, which is just like with an option, or I mean, a result is sort of that way, except a result is like either you have a result or you have an error usually. In either case, whenever you're handling that, like 99.9% of the time, the right thing is to match and then just handle both cases. And if it's a case where like you call a function and it returns a result or an option, then you just handle it once, and that's that. Now with result, of course, you can use the question mark operator, like you mentioned, which is already also really useful, and you can essentially use the call stack as like a way of sort of handling exceptions. Rust doesn't have exceptions in like the like Python or Ruby or C++ way, or like Java or anything. But you can basically emulate the behavior of exceptions, at least sort of logically speaking, by always having functions, or having functions that might fail return a result. And is a general rule, like, yeah, if your function call might fail, it should return a result. If your function call doesn't fail, then it should just return a regular thing, right? Like a string or an integer or whatever it's returning.
The other thing that's interesting too that I started, so like I said, well, before the show we talked, and I told you I basically read everything that was available. It's only the first 4 chapters at the time of this recording. I think that was something that was also really interesting to me, which I didn't know. I believe you said that you should implement the from trait. So you like I always heard that you should create your own errors, but I didn't really understand how and why and what this kind of stuff actually works. But and how you would do that, because you have other errors you have to deal with. And then there's the from trait, which makes it super easy to do, right? Because you could just say, okay, from, and then this outside type, and then how it's going to go into the type that you have right now. That is the most interesting one I think I've seen.
The from trait, which you can use with into, like dot into, the function. I would say the from trait is probably like the one trait you would end up using the most, because it's the best way to like convert between different things, and error handling is a great example of that, right? So like if you're calling a function that is in some library or something, and it returns a result, and you don't want to like deal with handling the error, you just want to use like the question operator to get the value out and go about your day, then all you have to do is implement the from trait that converts that error into like your own error type, basically, and you'd have like a message in there, or error code, or whatever you're doing, and so long as you implement that in a way that makes sense for your program, then you don't really have to worry about what the function is returning for the most part, right? Like it'll sort of bubble up the chain, so to speak, when there is an error. that said, like it's not magic. Like you still need to think about what happens when there are errors. Like sometimes you can just kind of ignore errors, and sometimes you have to actually handle errors. It all depends. But yeah, the from trait is super useful, and it's really easy to implement too. Like once you do it a couple times, it's like, oh, I get it. This is really easy.
And what I also thought was interesting too is that the from trait, if you implement that one, I think you said you automatically get the into trait kind of implemented
Yeah.
for you?
So they are the from and into are no, I'm not sure what the right word for them is, but they're basically like opposites of each other, right? And you can derive into from, and I guess vice versa. Actually, I don't know if that'll work. I'm not sure if you can implement into and then get from out of it. Maybe, probably. I think you should be able to. It might just be more clumsy. But anyway, generally, you'd never implement the into trait directly. You would just implement from, and then the compiler can just kind of figure out what you're trying to do from there. And then, yeah, that gives you like dot into, which is something like you'll probably end up using or seeing pretty often, right? Like an example would be when you have, I don't know, like when you have like two related types and you just want to like convert one into the other, a lot of types have automatic conversions, and they're usually implemented using the from or the into trait, and so you can just do like dot into, and it handles the type conversion for you.
I'm just trying to think about, I mean, I can always see into, but I'm just trying to think about like the from. So for from, like, what does the benefit? So I know from it kind of gives you all that. Is it because that like when you define your type, you don't have to do impl blocks for types that you don't actually own? Is that why it's the point of having the from? Or is that kind of to keep everything in line with, okay, here's my example error type. Now, if I want to go from this type to here, like it's kind of all together.
So if we're talking about errors, if you think about the case, so it was a pretty common thing is to use some library, right? And most of the time, libraries are going to implement their own error types, right? So suppose you have like an HTTP library, and you make an HTTP request, and then it returns a result from, like you make an HTTP GET or something, and it returns a result from, like it returns the result of the request, let's say. In the case that there's an error, you're probably going to have some type of error object or struct from the library, and it's going to contain information about what went wrong in the request. Now, that error struct from the library, like that code is that belongs to the library, and you could certainly like hang on to that struct and like pass it around in your code, but most of the time what you're going to want to do is take that and put it into your own error struct, or even maybe like put it into like a generic, like one of the standard library error structs or something, and then you're going to want to like deal with that, and the reason is because you have to be like if you're returning, say, a result from a function, you have to specify what the type is, and if the type is something from outside your library, then like that's or outside your code, that's, I don't know, it's just kind of weird, right? Plus, you probably want to have one struct or an enum for handling all of the different errors within your code. regardless, like not just network errors, but like someone inputs bad data or whatever it is. And way to do that is to have like an error struct or an enum that contains all the different types of errors and classes of errors, whether it's a network error, input error, or whatever. So doing that type conversion lets you encapsulate different types of errors, particularly errors from outside your code, into your code, and handle that in a sane way, I guess, if that makes sense.
Yeah, definitely. The other thing too, there's also try versions of these, right? So how does that work with try and the not try? So I understand that well, I guess the try must have to return an option, right? It either works or doesn't work.
Try, I believe, returns
a result.
A result. Yeah.
Mm-hmm.
Yeah. I mean, the normal into always returns a result. There's no like the conversion has to succeed, basically. The try version is like it could fail. In the case of error handling, converting error types should never fail. That shouldn't happen because when things go wrong, you don't want your code to also blow up in the error handling, because then you'll never figure out what the original error was. You'll just be like, oh, there's a problem in my error handling code, but I don't know why it blew up because it's in my error handling code. Try into, like the try from, the most common place you see that implemented is during type conversions where it might not succeed. Like, for example, suppose you're trying to parse a string into an integer or something, right? Like you have a string and you think it's an integer, so you call try into, and like if it succeeds, you get the result. If it fails, it returns an error. Like if you've got a float instead of an integer, or the string is just like letters or something, then try into will fail. That's a pretty common kind of pattern where you would see that. You can also, you can also use try into to basically test to see if a conversion will succeed, right? But the from and into traits, or try from, try into, are all about type conversions. But you're right that like it's broken into the two classes, I would say. One being conversions which have to succeed or always succeed, and the other being conversions that might fail for some reason.
Yeah, that'd be really odd if you did like the try from and then you had an error that you're converting into, and the error would error when trying to convert to another error. That would just be very difficult to manage, I think.
Yeah. I mean, yeah, I think you could theoretically like you could use that in your error handling code, but you shouldn't. Like the trait, the from and into traits, like they don't return an option. So like it won't even, like you have to return something. It won't compile even if you aren't. Rust makes it pretty hard for you to do it very wrong, I would say.
Yeah, that's kind of the beauty of like borrow checker and all these other kind of tools that are built into it. It's like if your program runs, at least you can guarantee it's going to run. It may error or panic, but that's not due to something else, like, this weird undefined behavior like you do with other types of programs.
Yeah, I mean, Rust is pretty nice about that. The compiler can't help you much with logic errors, but it can tell you when you're doing something that is sort of programmatically or maybe computationally wrong. And the cost of that is just that it's harder to sometimes do things in Rust right? Like, for example, in a language like Python, you can do things pretty wrong and it'll just kind of let you do them. And sometimes it's not a big deal, really, right? Like, just as an example, in a language like Python or Ruby, like often there'll be values that are empty, right? Like imagine you're reading in a bunch of JSON or something, and there's like a bunch of fields you don't care about, and like they're null or empty or whatever. Like it doesn't matter. You're not going to read them. You don't care about them. So like you don't have to handle them. You just want to parse the data, let's say. In Rust, on the other hand, you need to like worry about all those things that you don't even really care about, because the compiler cares about absolutely everything. So, I mean, in the case of like JSON parsing, there's libraries that'll handle that for you. But, for a lot of the basic stuff, which is like converting a string to an integer and back, sometimes it can just kind of feel annoying or clumsy in Rust, because it's like you always have to worry about that. Whereas like in Python, you can just be like, here's my string, make it an int. And like, if you're going to have an int there most of the time, then like you just don't care and you can just sort of force it. And Python lets you do that. And most of the time it's okay. Of course, like the counter argument to that is that like when it does blow up, it blows up catastrophically, which happens a lot, unfortunately. And of course, that's why Rust exists, right? Rust is like the antidote to those problems, basically.
Well, I mean, that's one of the things that really drew me into Rust, because once I heard that there's no like null, I was like, well, this is great, because null is such a pain in the ass, like in nearly all languages that have it. It's not the only language that has this kind of idea, but the fact that it's similar to C and C++ and to the runtime and things like that is huge. Then I think the next thing that got me was the memory safety and the freeing issue, which is always something that freaks everybody out, I think. At least for me, definitely freaks me out. But what else I see recently is now there's actually other languages that are kind of similar with this idea of like null checking or some kind of absence of value checking. Like for sure, Dart came out with null safety in their code. So if you have a question mark at the end of a type, that means that this thing can be null. And what's nice is that the compiler will actually force you to check it. Similar to Rust, where you have this idea of kind of like a union type, where it's either the result or an error or something like that, or something or nothing, right? With the option type. I think that's super huge. And that one definitely throws people off because so many few languages have this kind of thing.
Yeah, I don't know if Rust was the first to sort of have this philosophy, but yeah, nowadays a lot of languages have sort of been borrowing this idea of like better ways of handling edge cases and errors. Yeah, Dart is one. I don't really know Dart well, but another is Kotlin. Although I don't know, does Kotlin predate Rust? I'm not sure.
Kotlin predates. Oh, Kotlin and Rust. Oh, they're talking Kotlin and Dart, but Kotlin and Rust, I'm not too sure. Good question. Rust has been along for a long time, but not in its current form, right? So,
I think it probably showed up after Rust, if I were to guess, but I don't know.
So the first release of Kotlin. No, sorry, go ahead. Let me look this up. This is bugging. July 2011 is when they unveiled Project Kotlin from JetBrains.
Yeah, so I guess Kotlin came out right after Rust, then, like a year after. But yeah, I would say Kotlin, Dart, even Swift. Swift is another one that Rust influenced quite a bit. I don't know if Apple would ever admit. I mean, I actually don't know how like Swift came about, but my knowledge of it is that it's like an Apple project. I don't know if Apple would ever like admit that it was influenced by Rust, but pretty sure it was. And what else? Zig is another one that's like borrowed some ideas from Rust, but also like gone its own way. And Zig is like another one that is similar to Rust in that it's meant to be sort of I guess Zig is probably meant to be more of a lower level language than Rust. And, I think it's mainly supposed to be for like embedded or, I don't know, maybe like device drivers or something, I guess. I'm not exactly sure. I'm not a Zig expert, but I know Zig has a bit of a following as well for the same reasons as Rust, in that like the language makes it easier for you to, or rather the language makes it harder for you to write software that doesn't work, basically.
Yeah, I know the guy who wrote Swift is one of the guys who went behind LLVM, which is interesting too. So I'm wondering if LLVM was some kind of, I don't know. It's weird that LLVM and then Swift and Rust, right? This weird kind of relationship where they both have this kind of idea of checking for null values. Maybe there's something there. I'm not too sure.
Yeah, I don't know, but I will say that none of these languages would probably exist in their current form. I mean, maybe they would exist, but they probably wouldn't be as far along as they are today, if not for LLVM. LLVM basically makes it really easy to write compilers and build your own languages, which is why we've had like this sort of explosion of languages over the past, I don't know, 10 years or so. And now, I mean, I can't even keep track of all the different ones, but I think it's good. I think it's good that languages are always improving. I'm also still surprised that things like C++ are still so popular as well, which is interesting. I mean, C++ is interesting because they keep bolting on all the features get added into other languages, and then they like figure out a way to bolt it onto C++. And when I used to write a lot of C++ back in the day. Nowadays, when I look at C++, I just am like, what is going on here? It's just funny because like the syntax has become so complicated in an interesting way. In an interesting and I would say not good way. Not good in that like the language is so complicated now that it's almost like it doesn't even make sense anymore. If you're trying to use all the new features and stuff. I guess the problem with C++ and even C for that matter is that they've always tried to maintain the backward compatibility. So like they end up doing really weird things to sort of preserve the old syntax, but permit new syntax and new features. And kind of just makes a mess, I guess. Nice thing about Rust, and on the other hand, is that they haven't really tried to maintain backward compatibility, which I think is good. I don't really think there's any reason to maintain backward compatibility within between major releases of the language. In particular, if you're able to just provide a tool that converts the code from the old code, like the old syntax to the new syntax, and like you upgrade, you run the tool once, it changes your code, and then you're done, right? Like with Python, for example, when they did the like 2 to 3 conversion, they provided a tool that converts all the Python 2 code to Python 3, and you just run the code once, and now you're on Python 3, which is nice. I'm actually a big fan of like opinionated tools which is something that these sort of like older languages have refused to embrace. Maybe not as like, I'm not saying there's a conspiracy or anything, but just as a general rule, like 20-year-old C++ code will still compile today with a modern C++ compiler. And I'm not sure if it should be that way. Hey, I guess there's a strong case for maintaining backward compatibility, but I don't know. I think it's a somewhat weak argument in the age of LLVM and all that.
Well, so maybe the terminology that you use, I think, could be a little bit misleading, right? So I think when you're talking about what evolution of the language, you're talking about evolution of the addition, as Rust calls it, right? The way you write the syntax and which keywords are added, removed, etc.
That's right.
I mean, there is kind of backwards compatibility, but like it's different. Like where you could still use the old addition, but you have to like make that clear in your file, right? That this is 2018, but I think it's 2021. Like that's kind of the way that they kind of remain backward compatible. Like because the thing is, it's if you say it's not really backward compatible, that could be a little bit misleading because like that's one of their pillars, right? Is that okay? Code that was 1.0 and onwards should always run, and that's something that they're really sticking to. And like, it's kind of crazy all the effort that they put into it, and it starts to kind of remind you, maybe kind of reminds you of like the C and C++ where they try to keep things around. I mean, they're trying to keep things around because of that reason, right? Like going back and rewriting all this stuff because the tools maybe I heard they're pretty good for upgrading your edition. But I mean, there could be a time where it's like I just cannot upgrade for whatever reason.
Yeah, that's right. You clarified on a thing that I sort of glossed over, which is right. I mean, to compare it to C++, right? Like there's basically like the different versions of C++, right? Like C++ 21 and I don't remember like all the versions, but as far as I know, I mean, I think it's like come up as a debate more recently in the C++ community, but as far as I know, to date, it's still true that like, you can go and get like Strausrup's like original C++ book and take the source code from that and compile it today with like the latest Clang or GCC. I believe for the most part, right? Like, that is true. Well, okay, it may not be 100% true, but for all intents and purposes, like for the sake of my argument, let's say that that's true. Whereas with Rust, you can't take like Rust code from the first release and it's not guaranteed to compile with the latest edition. And that's because they basically looked at the language in the past and said, okay, here's a thing that was wrong or didn't make sense or shouldn't be there, or whatever. And, in the new edition, it's going to be changed or gone or whatever. And so, it's true that yes, you can just like configure your project to be compatible with, the older Rust edition, but like there's sort of like this idea that like once you upgrade, we're dropping the support for whatever the thing was that we realized is a bad idea, basically, right?
It's also interesting to kind of see. We had somebody on here. The name is losing me because it's still early morning for me over here. My coffee hasn't kicked in yet. We had somebody on here talking about 2021 edition versus 2018. And the most interesting part was like, they learned a lot from 2018 edition because that one was really brutal in terms of like the effort involved because they were trying to coincide edition change with a big feature, which is the async await, right? And for this next one, they didn't do anything like that. But I also don't think there's anything really big coming out. I mean, async await is huge, right? That's a huge piece of the language that came out. But for 2021, I don't think there's anything really big. But one of the other interesting things that they also did was they had like a new syntax where it's like, okay, if we prefix the something with something, then you get like it's already reserved, which is interesting because they want to be able to try somehow reserve keywords in the future. So they tried this kind of method. So it's very interesting to see how. So not only are they making changes, but they're also thinking ahead and learning from their mistakes. Like, okay, this was a bad idea. How can we solve this? Let's try this. And I don't know if this is going to work out for them or not, but I think it's better than keep doing the same thing over and over again and hoping that the next time will be better.
Yeah, I mean, I don't know. I don't have a crystal ball, so like I don't know how it's going to be in the future. But I've really enjoyed working with Rust. I think the language is always improving. The libraries are always improving. The tooling is really good, I think. And keep in mind that like the tooling is all based on LLVM. And so really it's sort of like inheriting what's good about LLVM. And in that sense, like, Rust is, I would say, as good as any language that also uses LLVM. But, like the Rust ecosystem, like all the libraries are, I don't know if anyone has like tried to quantify that, but I bet that like compared to like a lot of the other languages, Rust is probably the farthest along in terms of having like breadth and depth with all the like all the libraries and whatnot. And that, I guess that might not be true if you're talking about mobile platforms like on Android or iOS, because they already come with like very full featured SDKs as well. But even those, I think, probably don't compare to the whole like Rust crates ecosystem. So I think that's pretty unique.
Yeah, this is true. I mean, I think that's the benefit of these recent languages is like they lead on new technology, LLVM. That's pretty decent, it seems. And they also learn from the past and make good changes, right? Like this borrow checker idea. It's definitely not new, but just nobody really implemented it, or the few languages that did, nobody really knows about. So it looks revolutionary, but it's actually pretty old ideas and old theories, but it's still interesting nonetheless. I want to kind of get back to your book. And what I thought was super interesting is that you introduce a lot of components, which I think beginners don't really know about, right? Clippy is probably more well known, but you also had a couple others like the cargo expand, a couple other things like, these are good. But I think the weird part is like, why don't we just include these by default? Like, why do we have to manually add these in and try to remember to add these kind of things in?
Yeah, that's a good question. I think the philosophy in Rust is that everything should go into its own crate, either as a library or as an executable, and everything should be a bunch of separate crates. It's sort of like it's I guess it's similar to like the mono repo versus like lots of small repositories. If you're talking about like version control, right? Should you break everything up into a bunch of libraries, or just have like one super application or super repo or something? And there are pros and cons to this. One of the cons to having everything as like a separate component or separate crate is that you can often end up with packages or applications that break because like an API changed somewhere and they need to be updated. That unfortunately happens quite a bit. In fact, like I remember reading an email or something from Linus Torvalds of the like Linux kernel maintainer, and he was talking about this and how the reason why they require all of Linux has to be in one source code repository, like all the drivers, it's all in one place. And the reason for that is that when you have a really big project, it's much easier to maintain everything when it's like all in one place, and like everything has to run through the same suite of build tests and whatever integration tests. Whereas with Rust is like kind of like the absolute extreme other end of the spectrum, where for the most part everything is its own separate tool and package. And we're talking about editions and how, okay, what happens when you upgrade Rust Edition? Well, when you have lots of different individual packages, that's actually kind of problematic with libraries specifically, because if you want to use, the latest Rust Edition and you have a library using an older Rust Edition and it's not compatible, then you either have to get that library updated or find a workaround or rewrite the library or something. And that's, I actually haven't had much problem with that, but I've definitely bumped into things like that, edge cases, and usually not with like Rust editions, but with different libraries being incompatible specifically. So like this is an issue I talk about in the book, where you can have two libraries that have the same dependency, or like your code and a library you're using depend on the same library, and then there's like a version mismatch, and you can have a conflict. And currently, there isn't really an easy way to resolve that, and that's quite annoying. This is also a problem like in Java, for example, and so the way that you can work around it in Java is that there's a way that you can specify, you can like relocate the dependencies, or you can build like shadow jars. I don't know if you're familiar with this, but you can basically instruct the compiler to like rewrite the names of the functions that it's calling and whatnot, so that they don't conflict with like a different version of the library. And then you can actually include both dependencies separately within the same jar in Java. And then, the code which knows which functions to call, and like which versions of the libraries. So that kind of stuff is, as far as I know, still missing in Rust. And there are some examples of that, like where it's sort of rough around the edges. But I would say like I haven't found those kind of problems to be blockers in any way. I guess I think that was a bit of a tangent. I don't remember exactly what your original question was.
Yeah, I also forgot what my question was. There's more so another question that's kind of sticking out in my head, so when I read your book, chapter 4, you're talking about data structures. I think this one also talks a little bit about you use libc in here, or am I trying to use libc in 2 different chapters? But what I was kind of really curious about and really I have a hard time wrapping around my head is like, when should I use libc, and do I actually have to use libc? Because like,
Yeah.
or something like that. Because, and also you talked about adding and not adding in the C runtime, and like Muso doesn't add in C runtime by default. So I just get confused, because you always hear that C compiles down to like low level machine code. There's actually no runtime, but then you're saying there's a C runtime, and I think the C runtime will come from like libc or some kind of other compatible.
Yeah, mm-hmm. Yeah. So good questions. So I think in the book, when I include like, when I'm talking about like the C APIs, it's usually for the FFI, like the basically the foreign function interface, when you want to call like a C function for some reason. And FFI is sort of, I don't think it's like a real standard, but it's basically the standard for doing like interlanguage interoperability. So like, if I want to call a C function from Rust, or if I have, suppose I have like some Python code and I want to call a function in Rust from Python, then, you'd use FFI. And FFI is just like a fancy way of saying, it's just like it's basically like what's the right word for it? A convention for calling functions in C. And so I think the examples that I use in the book for talking about the C libraries is just to get the compiler definitions for the C types, because like if I'm calling a C function with an integer, I need to use the C integer type. And the C integer type and the Rust integer type are two different things, and the compiler needs to know the difference between those. And so like converting between them is trivial, but you need to tell the compiler that like this is a C integer and this is a Rust integer. And so I think that's where I use it in the examples. And regarding like actually linking to the C library and stuff, I think like how you do it depends really on the environment, but like most of the time your code just links to the system C library. So like you're not actually compiling or including the C library as part of your Rust application. You're just going to like call out to the system C library. But that's not always true, because on embedded environments, for example, you sometimes don't have a C library, right? Like the C library, like the standard system C library, is a relatively high level library. And it's like, it's part of like the operating system layer. And if you're on like a Arduino or like an ARM, like some embedded device, you don't have a C library. You don't have malloc, generally. I mean, some of these like some of the like embedded vendors will like give you libraries that kind of like provide similar behaviors, but you don't have an operating system kernel, and you don't have all that overhead. So, in that case, those things might just be like placeholders, basically. Or, you can ship your own C library, right? Like the micro CLib or uclib, for example, is pretty popular. What's that other one? Musl, MUSL, I think, CLib, is used by Alpine Linux, which is like another C library. Like there's the GNU C library implementation, which is the most common one, and then Musl, and then micro CLib, which is like the embedded one. And so, which you use depends on the context. Sometimes you might not use any CLib though. But keep in mind, there's like the C library, then there's like the C API, which is like the language API, like the C types, like an integer, double, and then the Rust types. So the C API, as it relates to Rust and FFI, is mostly about defining the types. And then you have like the C library functions, which is like this, like malloc and free, or maybe like POSIX functions or whatever. So, I mean, you can go pretty deep on that stuff too. It's a bit of a rabbit hole, I would say.
I'm just wondering, like a long type is that may be 101. That may be basically like an int 128. Like we can't just use these directly. You have to use some kind of C runtime, and if you want to have FFI?
You can't, because a long, for example, is platform dependent, whereas like an int 128 is not, right? Like in Rust, an int128 is always a 128-bit signed integer. Whereas a long on a 32-bit system is actually a 32-bit integer, a signed integer. A long on a 64-bit system is a 64-bit signed integer. I think on 32-bit systems, I'm not even sure if you can use a 128-bit integer. Maybe I guess the compiler could implement it for you, but it doesn't. I guess it doesn't technically exist on a well, there's no such thing as a 128-bit CPU. Well, not like consumer grade as far as I know. Maybe there's like a one that exists somewhere in a laboratory or something, but or like some really obscure one. But yeah, like for 128-bit specifically, that's a compiler add-on, and I don't think 120-bit integers are in the C language standard. Maybe they are in the latest one, but if you try to there's no such thing as a 128-bit integer in like a C compiler from the 90s or anything like that. So Rust, on the other hand, has them. Yeah.
I'm just wondering, even if I wanted to transfer something like a U8, you'd also recommend using something like libc to do that kind of thing.
You don't have to, but you should. Actually, I'm not sure if you could probably coerce it in unsafe code in Rust. But for the purpose of maintaining portability, yeah, you should always stick to specifying the types explicitly, right? Like strictly speaking, a U8 and a character in C are like the same thing, right? It's just one byte. But there might be some sort of implementation detail with the compiler about how it handles it or something. I don't know. One issue, for example, that comes up every now and then is alignment, like byte alignment. And compilers generally handle that in a non-portable way, right? Like compilers generally handle it in their own way, and a different compiler will align the bytes differently. So this problem comes up if you're dealing with like C structs, for example, and you want to take a struct and just write the whole struct out to a file or something and then read it in somewhere else. Well, if the bytes aren't aligned in the same way and you have two different programs compiled with different compilers, even if they've got the same struct definition, they might not read in the same structure unless you explicitly tell the compiler, this is how I want it packed. And it's not something that people probably really think about most of the time. But if you ever do embedded programming, you'll definitely have to bump into this because if you have a fixed amount of memory and you're trying to pack bytes into a small space, then you've got to think about okay, how do I get my structs really small and pack them? And it's kind of like playing Tetris with memory, basically. And the alignment matters because CPUs can do things faster when the bytes are aligned the right way for that particular type of CPU. So, depending on whether you're on ARM or Intel or whatever, compiler's going to pack things in differently. And if you try to make too many assumptions, especially switching between Rust and C, or LLVM and GCC or whatever, then you're going to run into issues without a doubt. And so, yeah, I mean the C API stuff with the FFI is there to increase portability and make it easier for you to make your code work in a lot of different places, basically.
Okay. Yeah, thanks for that. That part always I didn't really understand for quite some time, but I mean, there's already a standard and a core FFI section, so it's good to have some more feedback about, okay, yeah, because if you're dealing with a constrained environment, yeah, maybe things are implemented a little bit differently for, 32-bit or even 16-bit CPUs, like you said. So that can make some sense. Okay, I don't think I have any more questions. Do you have anything you wanted to say before we sign off?
Let's see. Well, yeah, do check out my book. It's called Code Like Pro in Rust. I will say that it's probably not the right book if you're a beginner. If you already know Rust pretty well, even if you consider yourself advanced, then I think there's probably going to be stuff in there that you can learn from. But the right target audience for this book is people who are sort of just getting started with Rust and want to reach a high level of proficiency as quickly as possible and not have to spend a lot of time sort of mucking about or searching Stack Overflow to try to do like basic stuff that sort of seems really confusing when you're new to Rust, but turns out it's like actually pretty straightforward once you sort of get over that initial sort of steep learning curve. So yeah, I think that's it.
Yeah, I think your book is great. I couldn't put it down. I read the first 4 chapters. Just I'm not the kind of person to actually be able to read as much as I can, but for this one, I actually luckily had some time, and it was that interesting to me. So it really kind of spoke to me. I think mostly about the libc stuff because I'm taking a look at that recently, and yeah, I'm pretty happy with it. So as somebody who's definitely, I'm trying to be objective over here. It really is a great book, and I think it's well worth picking up and checking out. So thanks for coming back on, or thanks for coming on, not back on. Thanks for coming on. Maybe we can have you again in the future. It depends if you have something that you want to kind of spread or if I see something else going on your side. Otherwise, thank you so much for coming on. And yeah, check out his book. It's great.
All right. Thank you.